Terminology of polynomial functions. A polynomial is a function that can be written as f of x equals a sub 0 plus a sub 1 x plus a sub 2 x squared plus and so on plus a sub n x to the nth power. Each of the a sub I constants are called coefficients and can be positive, negative, or 0, and be whole numbers, decimals, or fractions. A term of the polynomial is any one piece of the sum that is any a sub I x to the I power. Each individual term is a transform power function. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. The leading term is the term containing the highest power of the variable, the term with the highest degree. The leading coefficient is the coefficient of the leading term. Because of the definition of the leading term, we often rearrange polynomials so that the powers are descending. F of x equals a sub n x to the nth power plus and so on plus a sub 2 x squared plus a sub 1 x plus a sub 0 a naught. Example 4. Identify the degree, leading term, and leading coefficient of these polynomials. A. F of x equals 3 plus 2x squared minus 4x cubed. B. G of t equals 5t to the 5th power minus 2t cubed plus 7t. C. H of p equals 6p minus p cubed minus 2. A. For the function f of x, the degree is 3, the highest power on x. The leading term is the term containing that power, negative 4x cubed. The leading coefficient is the coefficient of that term, negative 4. B. For g of t, the degree is 5. The leading term is 5t to the 5th power, and the leading coefficient is 5. C. For h of p, the degree is 3. The leading term is negative p cubed, so the leading coefficient is negative 1. Long-run behavior of polynomials. For any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. Example 5. What can we determine about the long-run behavior and the degree of the equation for the polynomial graphed here? Since the output grows large and positive as the inputs grow large and positive, we describe the long-run behavior symbolically by writing as x approaches infinity, f of x approaches infinity. Similarly, as x approaches negative infinity, f of x approaches negative infinity. In words, we can say that as x values approach infinity, the function values approach infinity, and as x values approach negative infinity, the function values approach negative infinity. We can tell this graph has the shape of an odd degree power function which has not been reflected, so the degree of the polynomial creating this graph must be odd, and the leading coefficient would be positive. Short-run behavior. Characteristics of the graph, such as vertical and horizontal intercepts, and the places the graph changes directions, are part of the short-run behavior of the polynomial. Like with all functions, the vertical intercept is where the graph crosses the vertical axis and occurs when the input value is 0. Since a polynomial is a function, there can only be one vertical intercept, which occurs at the point 0, a sub 0. The horizontal intercepts occur at the input values that correspond with an output value of 0. It is possible to have more than one horizontal intercept. Horizontal intercepts are also called zeros or roots of the function. Example 6. Given the polynomial function f of x equals x minus 2 multiplied by x plus 1 multiplied by x minus 4, written in factored form for your convenience, determine the vertical and horizontal intercepts. The vertical intercept occurs when the input is 0. F of 0 equals 0 minus 2 multiplied by 0 plus 1 multiplied by 0 minus 4 equals 8. The graph crosses the vertical axis at the point 0, 8. The horizontal intercepts occur when the output is 0. 0 equals x minus 2 multiplied by x plus 1 multiplied by x minus 4 when x equals 2, -1, or 4. F of x has zeros or roots at x equals 2, -1, and 4. The graph crosses the horizontal axis at the points 2, 0, -1, 0, and 4, 0. Notice that the polynomial in the previous example, which would be degree 3 if multiplied out, had 3 horizontal intercepts and 2 turning points, places where the graph changes directions. We will now make a general statement without justifying it. The reasons will become clear later in this chapter. Intercepts and turning points of polynomials. A polynomial of degree n will have, at most, n horizontal intercepts. An odd degree polynomial will always have at least 1. At most, n minus 1 turning points. Example 7. What we can conclude about the graph of the polynomial shown here. Based on the long-run behavior, with the graph becoming large positive on both ends of the graph, we can determine that this is the graph of an even degree polynomial. The graph has 2 horizontal intercepts suggesting a degree of 2 or greater, and 3 turning points suggesting a degree of 4 or greater. Based on this, it would be reasonable to conclude that the degree is even and at least 4, so it is probably a 4th degree polynomial. Try it now. Given the function f of x equals 0.2 multiplied by x minus 2 multiplied by x plus 1 multiplied by x minus 5, determine the short run behavior.